Oh, sound. Need sound for sure. And if I got enough battery, yes. Okay. Now, I remember telling you this. There's a little bit of maybe difficulty in vocabulary here between function and mapping. And if you remember, I said, I don't know if anybody remembers which way around this, I said mapping is a type of function or a function is a type of mapping. Which way around? Does anybody remember? A function, I don't know if I heard both answers at the same time. A function is a type of mapping. So a mapping is something more general, whereas a function is something particular. And in fact, we say function, but to give it its full name, we should be saying well-defined function. So a well-defined function is a type of mapping. So I'm going to show you 4 types of mappings, but not all of them represent well-defined functions. Only 2 of them actually do. So here are the 4 types of mappings, and I'll use the diagram to show you them. So the first type, who remembers the name of the set that you start with? Very good, domain. And then the set that you finish in? Codomain. So let's say here we got A, B, C, and let's say here we have W, X, Y, Z. So here's an example of one mapping. A goes to W, B goes to Z, and C goes to Y. Sorry, that's a little messy, but there you go. So X is not used here. This type of mapping is called a 1-1 mapping. Listen, what's wrong for me? What's wrong? You listening? Yes? This one here is called a 1-1 mapping. And the reason it's called a 1-1 mapping is for every one element you have here, you get one unique element in the other set. So for example, B goes to Z, and only B goes to only Z. And C goes to Y, and only C goes to Y. There's no repeat in here, okay? So 1-1 is like uniqueness. Each value that's unique goes to a value that's also unique. Or in other words, each different input goes to a different output. So this is called a 1-1 mapping. Okay, so the next type, I'll draw it underneath. A, B, C, and let's say again W, X, Y, Z. So A goes to W, B goes to Z, and C goes to W. What do you think this one might be called if the first one was called 1-1? One many. Yeah, because each one value here, no, sorry. No, wrong way around. Many 1. Because many values here could go to one value here. So for example, you'll notice here that A goes to W, but also C goes to W. So many values here can go to one value here possibly, and B goes to Z. So this one's called a many 1. Many values possibly go into one value. This is recording, isn't it? Yeah. Okay, it's going down. So that's many 1. Next one. A, B, C. Oh, I have 2. I'll keep it the same. W, X, Y, Z. So here, A goes to W. A goes to X. A goes to Y. Let's get rid of the C. Let's not put too many. Yeah, and B goes to C. Okay. Any ideas what this one might be called? One many, because one value here could go to many values here. And again, B just goes to Z. So this one's called one-to-many. So no prizes for figuring out what the last one has to be. Many, many. This one's a bit difficult to do. Let me think. A, B, X and Y. So A goes to X, A goes to Y. So that one, if I just had this, it would make it many one. No, one many. Now, if I do this as well, this makes it many, many, because you can have A goes to X and B goes to X, or also A goes to XY and B goes to XY. So you could have one value here going to many values here, or you could have many values here going to the same value. So this is the worst type of mapping. Many, many. So there are the 4 types. Okay? Yes? Alright, now a little bit of notation here. If I call this mapping F, then there's a nice way to represent what the domain and the codomain is. You write it like this. F goes from A to B over to X to Y. So this is a nice short way to represent to the reader what is being used as the domain and what's being used as the codomain here. Okay, write that down as well, please.
For all of them, right?
Yeah, for all of them. I just did the last one as an example. Got that? Yeah? Yeah? Okay. Now, some more definitions. So anyways, question 1 in your worksheet is actually just practicing identifying which of the 4 it is. Is it one, many, one, and so on. Number 2 is the more difficult one. So just before number 2 here, a definition. So a function is a well-defined mapping. And what on earth is a well-defined mapping? Well, a well-defined mapping is a mapping that is 1, 1, or what could we have? We could also have many 1. Yeah. So, if I say a function is a well-defined mapping, all I'm really saying is a function is a 1, 1 or a many 1 mapping. But often when you're talking about functions, for some reason, I don't know why, you don't call it a 1, 1 or a many 1 function. You describe it as a 1 to 1 function or a many to 1 function. So now our next task is, how can you tell a function is 1, 1 or many 1? So for example, if I said the function x squared, would anybody know what that would be? Would it be a 1 to 1 or a many to 1? Many to 1. But why?
Because, well, if you look at x squared on both sides, you get the same.
Yeah, so you're talking about looking at the graph, yeah? Any other more algebraic reason maybe? So what is 2 squared? 4. And what's minus 2 squared? 4. So you have 2 different values going to the same value. So this makes it many to 1. Yeah? Now what about the function x cubed? What would that one be? Ah, now you see, that would be 1 to 1. But let me try and help you with the graphs here. If a function is 1 to 1, I think Brendan spotted this,
That would be like a linear.
it needs to be always increasing or decreasing, usually, okay? So for example, x cubed, well, just x cubed would be, oh, that's terrible. There's x cubed. And then a function like x squared would look like this. So, if your function never repeats its height, so if you look here, yeah, what's wrong, Miranda? Okay, if a function never repeats its height, so see here, the height here is different to the height here, all these heights are different. This is negative, this is positive, they're all different heights. If it never repeats its height, we say it's 1 to 1. But if its height could be repeated, so in this graph here, you see it has the same height twice, then we say it's many to 1. So x cubed is interesting because x cubed by itself is 1 to 1, but if you had a cubic function like this, what the heck happened there? If you had a cubic function like this, would you say it's 1 to 1 or many to 1? Well, you'd say it's many to 1 because if I draw a line here, you can see its height repeats 3 times. Once, twice, 3 times. So the graph can be helpful, but there is another way to do it, and that's with a condition. So I'll write it here in the box, or, well, I'll put it in here. So this is the way we'll be doing it, or at least one way to do it. First of all, you start off with x1 not equal to x2. You don't know what x1 is, you don't know what x2 is, but they're different. That's all you know. They're different. If it's possible for you to make this equation true, then you say it's many to 1. And if you can't make this true, if this is false, this is then 1 to 1. So if you can get this, you've got a many to 1, whereas if you've got this one, you've got a 1 to 1. You start off saying this, and you see which of the two is true. Okay, so I'll give you an example now in a minute. Did you write that down? Yeah. There's also a second way to do it, and a third way to do it, and there's not really one way to do these all. Did you write this down? Yes?
Sorry, I can't see.
Oh, yeah. Okay. All right, so let's have a look at an example now. Okay. So first example here. So let's take the function fx equals 2x plus 1. And I want to check if it's 1 to 1 or many to 1. Now you probably know the answer already. Which of the two is it, do you think?
It's 1 to 1.
It's 1 to 1. So we need to check though. So we start off by saying x1 does not equal x2. And we want to see if it's possible that this could be true, f1 equal to fx2. Could this be true? Well, you got 2x1 plus 1 equals 2x2 plus 1. Well, you can see what happens here. What happens to those ones? Cancel. And what happens to the 2's? Cancel. So what are you left with? x1 equals x2. Now, is it possible for this to be true? What do you think? Like, could this be true? No, because our starting point is saying that they're not equal. So it's impossible for this to be true. So because it cannot be true, we say it is 1 to 1. Remember, false is 1 to 1 and true is many to 1. Yeah? You look confused.
But
All right, I'll do another example. I'll do another one. Scroll up to what? To this? Yes, Joseph? No? Do you want another example of this type, one-to-one? So, okay. Can I go down? Yes? Okay. Do you need to write this down, or can I go to a new page? You need to write it down? Go to a new page. Okay. So let's take here fx equals ex. Now before I start it, does anybody know what this could be from the graph?
It's one-to-one.
It's one-to-one because it's continually increasing. So let's use the formula. Step 1, you start off by saying x1 does not equal x2. And then the second step is you see if you can solve this. So, what do you get here? This would be e power x1. And then here, e power x2. Now, how do you cancel e? Log. So, I'm left with now x1 equals x2. Now, can this be true? It cannot be true. Why not? Yeah, because it contradicts the statement at the start. So that means 3 cannot be true, which means, of course, 2 cannot be true. So we have, therefore, fx1 can never repeat itself. It can never be the same value. And this makes it one-to-one. Fiend, are you okay? Do you need to go, or you're okay? No. Are you sick, or are you just confused? I don't know which. If you need to go, that's okay. Yes? Okay. Have I missed something today, or like, is everything okay with her? Is she feeling unwell, or does she have bad news, or both, or neither? Or she's not liking this class? Like, do you know any info?
Maybe it's random.
Thank you so much.
Avenue.
That's just a beautiful opening.
Stay quiet over there, okay? I'm trying to find something out. You don't have to tell me what it is. Well, I just need to know if you know there is a reason. There is. Okay. Right. Do you write that down? And then I'll do another example. Yes?
Won't it always be false because this is the sequence, it never changes?
No, we're going to do an example now where it could be true. So we could have many to one.
We always start with that they are not equal.
Yeah, that cannot change. You always must say they're not equal, and then you examine if the fx1 could equal fx2. Yes? In my which one? Oh yeah, because there's a +1 and a +1 on each side, so I just cancelled them out. If you want, you can think about the +1 going to the other side to become a -1 and cancelling that way. Yeah. Alright, can I do now a many-to-one example? Yep, okay. So next one now. Fx equals x squared plus 4x plus 1. Now this is a really good one. The reason I say it's a really good one is because we know it's probably many-to-one from the graph. It repeats its height. And you could be finished if you could figure out what x's you put in to make the same height. So like, for example, if I put x as 1, what do I get here? Let me think. No, hang on, let me think. Shh, this is required. If I put x as -1, what do I get? Can you tell me if I put x as -1? I get 1 minus 4, which is -3, plus 1 is -2. Let me think. Okay, and if I put in x is minus 3, what do I get?
9 minus 12 plus 1.
Minus 2, which is the same as the previous answer, isn't it? So one way you could be finished is saying f of minus 1 equals minus 2, and then f of, what was minus 3 equals minus 2. And then you've shown clearly it is many values to one value. Although that's ridiculous, because how did I figure out minus 1 and minus 3?
Yes.
Well, that's one way to do it, but of course, if it was like decimal numbers, there'd be no amount of guessing that could get that. So how did I do it? Well, like what I did previously. So let's have a look. So you start off by saying x1 doesn't equal x2. And then you put in your function, f of x1 equals f of x2. So then you get x1 squared plus 4x1 plus 1 equals x2 squared plus 4x2 plus 1. Now we have to do some cleaning up here. So what can I do with the ones on either side? What can I do with the ones?
Cancel them out.
Cancel them out. Now what do you think I should do to try and simplify this? Take everything to one side to make it look more like a quadratic, or as you said, Brendan, take the x1 out and the x2 out on both sides. So if I take it out on the left, I get x1 times x1 plus 4, yeah, equals x2 times x2 plus 4. Yep, good, okay, that's great. Now, this is where I ask you, is it possible to choose a value of x1 and x2 that are different, but make each of these equal?
Yeah.
What two values? 0 and?
And 1.
Nope.
Okay, it's gonna be, we just there's a 1 and minus.
No, not my numbers I picked.
0 minus 4.
0 and minus 4. If x1 is 0, what does the left-hand side equal? If x1 is 0. 0. No. Try me out. Hang on. Right. Left, right. Okay. So if x1 is 0, what is the left? 0. And if x2 is minus 4, what is the right? 0. Yes? Can you see why? Because what's minus 4 plus 4? Yeah? Are x1 and x2 different? So you have found two different values of x1 and x2 that make this true. Therefore, it is many to 1. So if you use x1 equal to 0 and x2 equals to minus 4, you get the result fx1 equals fx2, and therefore many to 1. Although these are not the two numbers I gave at the start as my example. So can anybody think of any other way to show it's many to 1, or to find numbers to show it's many to 1? Any ideas? No? Okay. Let me show you what I did in my head. So, if you were to imagine this graph here, it clearly has a minimum point. Agreed? So it is very, very likely that the value that is one space to the left of the minimum and the value that is one space to the right of the minimum will have the same height. The minimum here can easily be found by doing what? Derivative equals 0. So what's the derivative here? 2x plus 4. So that means x equals minus 2. So minus 3 and minus 1 are good values to try to see if your function could be the same, because they're the same distance left and right to the minimum. Now, of course, that won't always be true. What is a key assumption I'm making here about my graph?
It's one like
That it's symmetric. That's the same on both sides. If my graph did something weird like this, down to minimum and then it wouldn't work. Okay? Right? So, I mean, there's not one universal way I can show you here. The method I'm showing you is probably a good way. It's a reliable way. It should work in most cases, but in some cases there's easier ways to do it, like in this quadratic here. That derivative I did in my head. And that derivative method I think would be very suitable for cubics. Okay? Because if you picture a cubic, cubics are like this. How many minimums and maximums? One of each. So if you took this point and moved one to the left and one to the right, it possibly will give you the same value. Okay? But of course that's not guaranteed. But it's a good, quick check you can do to see if you can save some time on this question. Yeah? Yes. Anything else that I told the other students that I didn't tell you? I told you about the word onto last time, didn't I? Who remember what onto means? Oh dear. Onto, what's onto? Uh-oh. Onto, come on. Yes, onto is the range equals all real numbers, yeah. The most important functions you could be dealing with are functions that are onto and one-to-one. There are not many of them. Can anybody think of any function that is both one-to-one and onto? Abanu, listen.
yeah.
Did you hear my question?
It's one-to-one, and the thing is that I was there.
Were you in the last class?
No.
I'll try that again. So can somebody tell me any function which they can think of that's one-to-one and onto? Oh, you missed that class as well. You two can be quiet for the moment, okay? Anyone else over here? Yeah, well, give me something more in... No, not zero, no. Well, first let's start off with what functions are onto? What functions make all real numbers? Yeah, which one? Which, I can get one at a time. So, Fumi, do you know one? Linear, yeah, that's one of them. Is that what you were saying as well? Yeah. Anything else? No, quadratic can't make everything. Cubic would, yeah, and so on. Now, let's take linear. Is linear one-to-one? Yes, so linear is good. Cubic is onto, but is it one-to-one? No, it depends. It might not be, okay? Now, what about EX? EX is one-to-one? But is it onto? No. So there's not many functions. The only functions that I can think of, and it's important that you know, functions that are linear, what else did we say? Functions that are like this, ax to an odd power, like ax cubed, ax5, whatever. What else did I just say now? Cubic, no, that's not onto. Yeah, it's not onto. It is one-to-one, but it's not onto. Anything else? Not quadratic, not sine, not cos. Yeah, but only cubics are like of this form, ax cubed. Because if it was like this, it would not be one-to-one. There has to be more. It can't just be these two. What else? Sine, no. Cos, no. Tan, no. Log. Kind of. Log. Yeah. Log is onto and one-to-one. Good, okay. E, no. Square root x will do it. 1 over x, no. What else is left? Have I said them all? Yeah.
Wouldn't 1 over x be,
It's not onto because you can't make 0 with 1 over x. So it's almost onto. Except for that 0. Yeah, so as you can see, but you see, linear is almost the same as this, with just with an odd power. And this is also kind of just like a power as well, isn't it? So really, there are not many functions that are both onto and one-to-one. Onto and one-to-one. It's not a common thing you would see. There you go. That's your interesting fact for today. There are not many functions that are both onto and one-to-one. Huh?
wait, how does y equals square root of x take into account?
Wait a second. This isn't onto. Why is this not onto? You can't make negative numbers. All right, our selection of functions which are onto and one-to-one has gotten smaller now. Yeah. Yeah, that's really it. I can't think of anything else. You see, tan x is onto, but it's not one-to-one because sine, cos, and tan repeat. What else did I say? Ex doesn't make negative numbers. Square root x doesn't make negative numbers. 1 over x doesn't make 0. Yeah, it's not so many of them.
Isn't the log of x can be 0?
Well, you can't use 0, but I'm just talking about onto, which means could it make all real numbers? So if you were to look at the graph of log x, it goes like this, which means it could make all real numbers. It could be 0. To make a 0, you just use x as 1.
So what about straight lines along the x-axis? Would that count as onto?
Yeah, no, because I don't want this to be parallel, because then it doesn't make, it only makes one value. So if you want, you have to say here m is not 0.
You said it was the domain. Domain is the x. Sorry.
Domain is the x values, yeah.
Oh, okay.
And range is basically the y values. So
we're really looking at
the y's.
function,
Yeah. Okay, which one's to try now? Let's see. I have seen, both could be in the exam. Okay, linear, quadratic, cubic, 1 over linear, 1 over quadratic, e log square root log quadratic. Yeah, okay. I recommend that you do A to K in both. I asked the other students this yesterday, and you can give me your answer. Can I or should I assume that you're all wise enough and responsible enough to know what you should be doing for homework? I'll try not to look in this direction of the room. Would that be a yes or no? Like, I could assume that you would know what to do for homework. Or do you want me to continue recommending what ones you do? Which is it? It's up to me. Okay, what about this side of the room? Any opinions?
Yeah.
You have opinions? Great, all right. Well, that's settled, so. Okay. You can start those now. So, I think number 1 shouldn't take you too long to do. If you draw, I recommend that you draw each of them. Number 2 will probably take you some time, but number 2 is kind of more what you get in the exam, unfortunately. Yes? Oh, yeah.